Hello everyone. Today our group will be presenting comparison of Fibonacci heap and binary heap in Dijkstra's algorithm. Our group member includes myself, Karan, and Prapmeet. So Prapmeet will be taking over from here.
Good morning, everyone. Today we will be discussing on comparative analysis of two important data structures, Fibonacci heaps and binary heaps. Specifically, in context of Dijkstra algorithm, our focus is on how these heaps differ in performance and why this is significant for the real-world application. The goal of this project is to compare Fibonacci heaps and binary heaps, focusing primarily on their performance when used in Dijkstra's algorithm. Heaps are critical to many algorithms, especially those that require efficient priority queues, such as Dijkstra's algorithm, while Fibonacci heaps offer better theoretical performance. For certain operations, binary heaps are widely used for their simplicity. This comparison is crucial for understanding how these data structures impact algorithms' efficiency in practical scenarios. Now let's talk about why this comparison matters in real-world application. Fibonacci heaps, due to their decreased key operations, are practically useful in systems like network routing and GPS navigation, where frequent priority updates are necessary. On the other hand, binary heaps are simpler and more efficient for smaller data structure sets, making them popular for various implementations. So, understanding which heap to use can significantly impact performance depending on the problem at hand. Now coming on to what exactly is Fibonacci heaps? It is collection of trees where the parent-child relation are less structured compared to a binary heap, which allows for more flexible and efficient operation. For instance, Fibonacci heap allows for time complexity for intersection and decreased key operation. These characteristics make it especially useful for algorithms that rely heavily on these operations like Dijkstra's algorithm. On to the other hand, next, next let's talk about Fibonacci heap. A Fibonacci heap is a complete binary tree where each parent node is smaller than its children. It's a simple implement often using arrays and provides a balanced approach for many heaps operation. While decreased key operations are lower in binary heaps with an time complexity, that is O log n. They are still widely used due to their efficiency with smaller datasets and their simplicity in the implementation. Now that we have covered the basics of both heaps, let's dive into the Dijkstra's algorithm. This algorithm is designed to find the shortest path from a source node to all other nodes in a within graph. It makes use of priority queues to select the node with the smallest distance When using binary heaps, the O log n decreased key operation can slow down the algorithm in larger graphs. However, when using Fibonacci heaps, the O1 decreased key operation allows for a faster execution in dense graphs. So basically, for our experiment, the goal was to measure the performance of Fibonacci and binary heaps in Dijkstra's algorithm, especially for intersections, decreased key, and exact min operation. We used Python and a variety of libraries including heaps for binary heaps, operations and custom implementations for Fibonacci heaps. We also tested the heaps on different sizes of data to see how they perform under varying conditions. In this, we measured the time taken for each of the three key operations that are stated above, like the intersection, decreased key, and the exact min for both Fibonacci and binary heaps. The performance matrix focused on both time complexity and overall runtime of Dijkstra's algorithm across different graph densities. This helped us evaluate which heap performed better under specific scenarios and provided insights into how graph density affect the efficiency of each heap.
Hello everyone, my name is Balkar and I'll be taking over from here and I'll be explaining the code implementation overview. So for the development of this project, Python was the language of choice. We used different Python libraries, heap library for the binary heaps, random library for generating random data, time library for calculating the time, matplot library for plotting the graph in comparison used for Fibonacci, and a binary heap comparison using Dijkstra's algorithm, and network X to have a graph structure used in Dijkstra's algorithm which connects with matplot library to generate the graph. Over here, I'll quickly go through the key components. We have Fibonacci heap, binary heap implemented using Python heap library, Dijkstra's algorithm comparison test, a small real-world application which is a city map application. Here we have the user input take two cities and gives you the shortest distance between two cities using Dijkstra's algorithm and binary heap. This is the insert operation function in the Fibonacci heap class. A new node is created with given key and value and added up to the heap list. If there is already a minimum node, that is the min node, and the new node is inserted into the left of the minimum node. If the new node is smaller, it rises up to maintain its core structure, which is the tree structure. The time complexity is constant, so it doesn't affect the structure for the algorithm. Moving on, this is the extract min operation function. As the name suggests, it removes the minimum node from the heap list and the new minimum node is determined over here. The extract min operation removes the smallest element and then consolidates the heap structure. As you can see, the time complexity is log n due to the consolidation. Decrease key operation. The decrease key function decreases the key of a node in Fibonacci heap. If it checks if the first key is valid, then the key is updated. If it has a parent and the new key is smaller, the operation removes it from the parent and ensures that the higher nodes are adjusted accordingly to maintain its structure. The decrease key operation is also faster due to its constant time complexity, as it cuts through the nodes and adds them to the root list. This is the cascading cut function. This handles the multiple cuts in Fibonacci heap to maintain its structure. When a node loses a child and it's marked, if it loses another child, it's removed from the root list. Cascading cut function helps balance by moving nodes to the root list after multiplying child losses, and the time complexity is constant as well. Over here we have the real world application, which is the citymap application. As you can see in the code snippet, we have used the Python dictionary to create the graph, which represents the keys and values for the local city and their distances from each city. This program implements the Dijkstra's algorithm using priority queue to find the shortest path from one city to another city. As you can see in the output, it also accepts user input to give the outputs. It has backtracking to reconstruct the path for the city, and the time complexity is which is V is for number of vertices and E is for edges, which gives the graph for the program. This is the website tool which gives us a better understanding and visualization of Fibonacci heap. Also, credit to the person who created this. As you can see, the minimum node is highlighted at 2. If we delete the minimum node, it sets the new node to be 3, which is the minimum node in the entire structure. For example, if I add a new node which is 1, it sets that as the minimum node. So that means the Fibonacci heap balances its structure. So over here we can look on to my system configuration. The results are just for one explanation purpose. The observation and details will be covered by Karan. So for the operating system, that's the main purpose why I had this results. So there is a difference in the operating system. I have tested my code on Windows 10 and also Ubuntu, where I used Windows subsystem for Linux to get the results. I'll be talking about it in the conclusion as well. Here are the tools used for the development of this project, which is Microsoft Visual Studio Code for coding as well as debugging. I used its built-in debugger for getting the errors and looking through each step. Then I also used JetBrains PyCharm. This I used specifically because of the two libraries, which is Matplot and NetworkX. I was able to upload in the virtual environment and get it running easily just through the user interface. Then I also used the Tab 9 AI chat, which is also really good for coding. It gives real-time suggestions while you're writing, and also has generated the code for Fibonacci heaps. This is a really good tool for excelling your coding and development in the project.
Hey Professor, hey guys. I'm gonna be taking over from Balcars after he explains the code for you. So this is our results right here. So our heap comparison results, our the test conditions were the 1,000 elements. The platform we did it on was Windows 10, and the operations we tested was the insertion, decrease key, and extract min. The results that we got was the binary heap. The insertion was this times in second, and a slower decrease key due to the time complexity. But the Fibonacci heap was faster, and yeah, here's the time complexity on that. For that one, so our observation for this one was Fibonacci heap outperformed a binary heap in both insertion and decrease key operation. That was our results for the 1,000 element, and here's the screenshot of our the code, and it's pretty much the same thing what I had in the other code, and just telling us the times per all this. So the performance comparison, Fibonacci heap was this much, and this one's for that. Performance 1,000 decrease key operation. Here's that. Here's that. and go on for the next one. So then we did the heap comparison results with the 10,000 elements. Pretty much the same test conditions right here. The results that we got for the binary heap was 0.327 seconds, and the decrease key was the O log n. The complexity led to a longer execution time. The extractment was slower due to the rebalancing of the heap. And the Fibonacci heap insertion was 0.0178 seconds, significantly faster due to the O1 time complexity. The decrease key is faster, taking advantage of the O1 complexity. The extractment took slightly longer than the binary heap, but overall performance was better. So the observations that we got was the Fibonacci heap maintains its performance advantage as the data size increases. The gap between binary and Fibonacci heap becomes more noticeable with a larger heap, especially in the decrease key operations. Here's the screenshot for that. It's pretty much the same information that I had on the last slide. Go from there. And this is a test conditions for this the algorithm and the binary and heap Fibonacci heap. So the graph size was 5 verticals, 10 edges, and 10 verticals, all that. And the results that we got for the binary was the small graph was this many seconds, and the medium graph was a little bit faster. Performed well, but slower for the larger graphs due to the O log n decrease key. Uh, also, the Fibonacci heap with the small graph was 0.002336 seconds, and medium graph for 0.00255 seconds. Faster for the larger graph due to the O1 decrease key. The observation that we got was binary heap performed better on a smaller graph, and the Fibonacci heap outperformed the binary in the larger, denser graphs. So the learning experience, theoretical versus practical efficiency. While Fibonacci heap offers a better theoretical performance, we learned that the binary heaps are often more practical for smaller data sets due to the lower overhead. The platform differences with WSL showed slightly better performance than Windows 10, highlighting the impact of system level optimization. Challenges with Fibonacci heaps. Implementation Fibonacci heaps was complex, but it helped us understand dynamic structure and how to optimize the code for efficiency. And applying Dijkstra algorithm, the project reinforces the importance of choosing the right data structure based on the graph size and density in the real world.
So I'll be taking over from Karan and we'll be discussing the conclusion. So based on our performance data, we clearly see that the binary heap and Fibonacci heap has different performance based on the platform and input size. So on the Windows, it was 4.4 times faster compared to the binary heap, and on Ubuntu, it was 30% faster for Fibonacci heap and 25% faster for binary heap. While we was comparing for the Dijkstra's algorithm, we did found out that Fibonacci heap was slower than binary heap, even though in theory it should be better in terms of performance. So this happened due to the additional memory and pointer management in the Fibonacci heap, which causes slower performance in the practical use. Here are the references for the project. One of the references which I would like to highlight is from Seth Dev. This is a YouTube video which was provided in our assignment feedback from the professor. This helped me to concise all the information for this presentation. Thank you for watching our presentation. Hopefully you liked what we presented, and we are here to answer your questions. Please feel free to put down your questions as well in the discussion forum.